Welcome to qnawire.
Hi, so in this problem we're dealing with the following Hamiltonian that is given by 1/2 of p squared plus x squared. We are given the commutation relationships and the definition for the operators. P is equal to minus I times the derivative with respect to x, and the commutation relationship in between x and p is equal to I times the identity matrix, or I times identity as a vector, however you want to describe it. Both are valid. So we are told that we can get a pair of operators that are actually the ladder operators for the harmonic oscillator, which are described by the following: over square root of 2 and a minus, which is equal x plus ip over square root of 2. So the first thing that we need to do is to show that the Hamiltonian is equal to a plus a minus plus 1/2 of the identity. I'm going to use the same notation as in your book. So how do we show this? Simply, we can get the operation a plus times a minus. This is in other contexts labeled as the number of per operator because it tells you how much quantums you have in a state. So we're simply going to do the operations corresponding to this product times x plus ip divided by square root of 2. Remember, when we are doing operator algebra, we are not actually just taking like the difference of squares as you would do in other cases. First of all, 1 over 2, because of those numbers. The first operator that we're going to have is x squared minus plus I x times p minus I times px minus I squared p squared. First of all, we can already identify that this is equal to 1/2 times x squared plus p squared plus 1/2 of I times xp minus I times px. Let's factorize the I over here and put it outside this parenthesis. But what is xp minus px? Well, this is nothing but the commutator of x and p. Thus, since we already know what value is that, is I times identity, this becomes 1/2 of x squared plus p squared plus I over 2 times I times identity. This means that our operator a plus a minus is then 1/2 of x squared plus p squared minus 1/2 of identity. So how can I convert this into a Hamiltonian? Well, if I do a plus a minus plus 1/2 of identity, sorry, I keep using the 1 as identity, we're going to get 1/2 of x squared plus p squared, which is equal to my initial Hamiltonian. So we're done with the first part of the problem. Next up, we need to find the commutators of a minus and a plus. and of H with A plus. First of all, the commutator with of A minus A plus. This is going to be equal to commutator of X. Let's go back a little bit for the definition. A plus is with a minus is with a plus. So X minus I times P. Both of these are operators. Square root of 2 with X. Sorry, here X plus IP. And the next one, X minus I times P divided by the square root of 2. We are going to apply commutator rules. The constants go outside, so this is 1/2 of the commutator of X plus IP with X with minus IP. We can do this simply. We can simplify this further as, let's expand it as A, B, C type of commutator. So this is the commutator of X plus IP, sorry, with X, oops, minus 1/2 commutator of X plus IP with minus IP. Sorry, with IP, because I already took the minus outside of the commutator. We can expand this a little bit further. This is the 1/2 of the commutator of X with X plus 1/2, actually I over 2 times the commutator of P with X minus I over 2 the commutator of X and P plus, this plus comes from the minus over here, and I times I, which is I squared. I squared is minus 1, P and P. Out of these commutators, this is equal to 0, this one is equal to 0, and the commutators of Px and Xp are going to be, for the case of Xp, the commutator is equal to I times identity, and of Px, we simply switch it places, so this is minus I times identity. So the result of this commutator, this is minus I squared over 2 times identity minus I squared over 2 times identity. Minus minus 1, 1/2 plus 1/2. This is equal to identity. And we're done with this one. For the final one, we need the commutator of H with A plus. In this case, since we already did the calculation and we already know that H is equal to A plus A minus plus 1/2 of the identity, we can employ that in order to calculate the new commutator. Also, we know the commutator of A minus with A plus, right? So H with A plus, this is equal to the commutator of A plus A minus plus 1/2 of identity with A plus. Applying commutator rules, this becomes the commutator of A plus A minus with a plus 1/2 of the commutator of the identity with a plus. The identity commutes with all operators, so this is going to be equal to 0. So now we have a commutator of the type of AB with C. So remember that a commutator of A, B, and C, applying some commutator algebra, this is equal to 8 times the commutator of B with C plus AC times B. Let's apply these rules. The commutator, we take out the one on the left outside, and we have commutator of A minus with A plus plus. Now we keep the one on the left, and we take the other one to the other side. A plus with A plus, the commutator in between two operators that are the same is always going to be 1. Sorry, it's always going to be 0. So we have a 0 over there, and we arrive to A plus times the commutator of A minus A plus. But guess what? We already did the calculations, and that is identity. So we find the result of A plus. For the final result, which is part B of this question, we are essentially asked to find what are the ground state functions for this, because the problem doesn't explain this, but essentially the A plus and A minus operators are ladder operators that allow you to take one state of the harmonic oscillator and take it to, for example, A plus takes you from 0 to 1, and A minus takes you from 1 to 0. But A minus acting on the ground state, it is always going to yield a 0 value. It is called that when A minus acts on the vacuum, yields a 0 value. It doesn't give you any vector. So in this case, this is equivalent of saying that A minus applied to a certain function, I'm going to use this rho of x, it's going to be equal to 0. So if we take out the values for A minus, essentially our equation is going to look like x times rho of x. Remember, A minus was the one with a plus in the middle, plus I times p, which is minus I times the derivative with respect to x, this function, x. All of this is multiplied by 1 over square root of 2, and this needs to be equal to 0, right? Let's simplify this a little bit. This is 1 over square root of 2, x times rho of x, I times I squared with a minus with a plus, plus the derivative with respect to x of rho of x. And we can get the solution for this differential equation as, which is going to have a solution phi of x equal to e to the minus x squared over 2. And of course with a constant in front of it. How can we find this constant? Well, simply we need to satisfy the condition that the integration in all of the space of phi of x, phi of x, x, needs to be equal to 1. And that would be all for this problem. Thanks.